Hello again. We have another talk now from Jessica Clarke about CHERI and Morello. Jessica.
We're better now? There we go. Keep it. Oh, and of course then it picks it. Right. So this morning we had a great talk from Steve, a bit of architecture. Hopefully you enjoyed that because I have a lot more architecture for you now. So if you're scared, the door's over there, but hopefully you want to stay. So I'm here to talk about CHERI and more specifically Morello, especially given the venue here. So first the obligatory funding acknowledgements, many funding bodies over the years, many projects. This is a timeline of the project. You can see right the way over here, the very first proposal, this custard proposal, July 2020, 2010 even. We are now over here in 2023, and there's a lot that's happened, and it's still going on. It's exciting, there's lots to do, there's lots that's done, but it's a massive project. This is definitely not just my research. I came along somewhere in here, in the middle. I think maybe I'm past being here longer than I've not been here, but it's about touch and go. So, does anyone know, at the start of this month, 2nd of November, does anyone know what that was the 35th anniversary of? Has anyone read my abstract? Because the answer is there. Anyone? It is, in fact, the Morris worm. 35 years ago on the day of the 2nd of November. And in fact, a colleague was fortunate enough to be giving a talk on CHERI on that day in 2023. And the Morris worm had 4 different avenues of propagation. Some of them are just the more classic sort of authentication issues, you know, trusting hosts implicitly, username password reuse and being able to crack them. One of just you had sendmail had debug commands enabled and you could just inject over the network any commands you wanted. Most hosts didn't have it, but some did, and turns out that's a bad idea. But the main one of interest is the 4th one, fingerd. Hopefully we've heard of fingerd, maybe a little bit lost by the wayside, but there was a buffer overflow there. In fact, it was a very stupid buffer overflow using the highly unsafe gets function in C. But buffer overflow, something 35 years ago. This is one of the most well-known first examples of it, but 35 years later, we're still facing this issue. So on Thursday night, I took this screenshot of the Debian Security Advisories page, and I think that's 11, 12, 13, something on that order. And you can see we have 5 of them are buffer overflow style attacks, and 4 of them are use after free vulnerabilities. In fact, some of them have multiple within the same DSA, but the point is, just within, you know, a few weeks of DSAs, we've got many of these instances showing up still 35 years later. So the problem really today is that pointers, they're just integers. They're an address, right? They point to somewhere in memory. We go, we do a load, we do a store, and the processor is checking, is memory mapped there? It has no knowledge of what that pointer means to me, the software. Now, Steve is talking about how some of the schemes we try and introduce some of those knowledge into it, but we're constrained by the fact that we're still trying to fit everything into this 64-bit address. And really, the hardware still doesn't, it can maybe understand there's like a pack key or something, but it still doesn't really understand what that means. So it's very difficult to get robustness there in our unsafe languages. So we have these problems, right? We can forge them, we can inject them, as we see with the return-oriented programming attacks. And there's no intent conveyed down to the hardware, just that this address is a thing that's mapped. Something in that process is allowed to touch that memory, and so the hardware says, okay, I guess you are allowed to do that, whether or not you were that part of the process. And so we have various schemes. We've seen BTI Unpacked this morning, and Shadow Stack is the bonus that I didn't think would be on there, but now is, but I've helpfully covered it as well. There's also MTE, which is trying to do more of a sort of data side of things rather than the code side of things. But all of them suffer from the fact that they're trying to retrofit a bit of security into this integer address. And so they suffer from normally at least one of these problems. So things like PAC and MTE, they're relying on some kind of probabilistic mechanisms ultimately, because you have this cryptographic key, maybe it's big enough that the probability is fine, but ultimately there's a probability that you happen to be able to inject the right value for that key. Sometimes they're relying on secrets. In the case of PAC, right? If you leak that encryption key, now anyone can forge anything that they like. Same you can kind of see with MTE, but it's a very different design, and I'm not really going to talk about that, but it's quite an interesting approach as well. And generally, they're often targeting the symptom of the problem, not the cause. So BTI is not stopping you doing the overflow. It's just catching that when you've done the overflow and then try and do a jump, ooh, something's gone wrong earlier in my program. But I'm still able to corrupt data. So maybe we can stop certain avenues for that exploitation, but the general problem of having that vulnerability in the first place where we can do this corruption still remains. And so maybe we want to try and do something about that instead. Or maybe they sort of target a cause of the problem, but it's not really the root cause. It's sort of a step along the way rather than the final part of the chain. So our solution is to change the world. We change the fact that addresses are just integers, and we want to bake in additional information. So we have here, alongside the 64-bit virtual address, we now add an extra 64 bits. So the primary one is bounds. So your allocation has a certain size. We would like to tell the hardware that is the size of this allocation. Any pointer to that allocation, any offset that you derive from it, all of those will convey the bounds of that original allocation. If you try and go outside those bounds, the hardware knows it will trap, even if something else is there. We also have permissions, so we can do things like you see with page tables today, where you can do read, write, and execute permissions. We can do the same thing in this metadata for our capabilities. We also have this thing called an O-type. This is not really discussed much today, but this is some notion of sealing. So I might want to hand you a pointer that you then later give back to me, but I don't want you to be able to do anything with it. I just want you to have that as an opaque token. I know what it means, and I have the ability to use it because I sealed it, but you didn't. You can't use it. You can just give it back to me, and if you try and do anything with it, it's going to clear this extra tag that we put on the side. And this tag is important because it's trying to protect all this metadata, because it's all very well and good having your bounds, having your permissions, but if I can just go and write to memory and overwrite them, I'm protecting some kinds of attacks, but ultimately I can still inject those things in the first place. So this tag lives on the side, and the idea is the processor is keeping track of every single capability in the system, whether it's valid or not. And so the only way I can get valid capabilities is I start with an existing valid one, and I perform some very explicit operation, whether that's pointer arithmetic, whether that's restricting bounds, restricting permissions, and that gives me, as long as I've not tried to increase bounds or increase permissions, that gives me another capability that still has that tag set. Anything else atomically will clear the tag along with whatever operation I was trying to perform. And so we can see here on the right, this is some kind of reflection of what you might see in a program, right? You have your allocation, and then the bounds are expressing this lower and upper bound, and our address is somewhere in between, we hope. And then everything's good. So in terms of the hardware then, so our registers that were just our 64-bit integers, now we've extended them to be, well, 129-bit capabilities, 128 bits plus this extra tag. Similarly, all these system registers that we have that maybe you don't think about as the applications programmer, things like the exception register. So when I would take an exception, I need to know when I then return back to user space what capability I need to use. We have this special DDC register, so we want to maintain compatibility with code that's not using these capabilities. And we don't just want that to be a massive hole in the system where suddenly you can do anything you want. So if you use an integer, there's this extra special capability register on the side that's saying what can those integer offsets use. So implicitly, you can think of this as being sort of the metadata part, and then every time you use just an integer for your operation, it then substitutes in the address alongside that metadata and glues it back on. So that allows me to constrain any code that's not using capabilities what it's allowed to do. And in memory then, well, obviously we need to store these 128 bits of capabilities, but we also need to take care to store this tag. So we have to have some kind of tagged memory, and we add 1 bit for every 128-bit word alongside it that you, the programmer, cannot explicitly access. The processor is managing it for you behind the scenes, and it's very important that that's protected. And so, yes, so there are all kinds of parts of the architecture that we do touch. So page table permissions, we want to add new bits to constrain how capabilities can flow. We have new exception codes for when you start to do out-of-bounds accesses. We mess with the exception interrupt flow because we have, well, we have this extended exception register, but also the register that you're using to jump to your exception handler, that itself also needs to be a capability to tell you what the bounds of that code is. And so everything that was an integer that is sort of somehow referencing memory now becomes a capability in our system. So in terms of hardware, back in 2010, this was done based on MIPS. MIPS was still just about fashionable back then for research. It was about the only option if you wanted something that was sort of permissively available, especially in the context of patents. These days, as I'm sure most of you are aware, MIPS is dying, thank God. And so we have also moved away from MIPS. So we've moved to RISC-V, has its own issues, but it's better than MIPS. So we have currently 3 different open source implementations. We have one that's a 3-stage pipeline, one that's a 5-stage pipeline, and one that's trying to be some kind of out-of-order core. It's obviously not going to be high performance. It's not high performance like a commercial processor, but it's good enough to do the kinds of research that we need to do. And these are all built off existing off-the-shelf cores that we've just taken and extended. And as part of this, we've had various contributions to academia. So this, on this slide, right, these bounds, logically, that's a 64-bit address, that's a 64-bit address, and that's a 64-bit address. But you don't want to store 3 times 64 bits just to store all that information. And the observation is there is a lot of redundancy because your bounds and your address are all going to be quite near each other. So we instead do some kind of floating point representation where the bounds and the address all share some upper bits that say this is the big region, and then within that we have some exponent, etc. So we lose a bit of precision in some cases, but that's fine. We just round up the size of our allocations. So that's one aspect that we've had to explore. Also tag memory. Back in 2010, MTE was not a thing. These days, MTE does exist, so there's been some more work into tag memory because it also needs that for different reasons. But we've had to work out how to do efficient tag memory, both on commodity cores and on a system where you're able to more tightly integrate with the memory controller. So all our designs are open source, and we also have emulators. So you don't want to run on a 25 megahertz FPGA all the time, or 100 megahertz for some of these simpler pipelines. It's okay, but I/O kind of sucks and performance kind of sucks. So you really want to do most of your development in an emulator. So we have QEMU, as most people do. It works pretty well, and it's generally what we'd historically do a lot of our development on. And then in terms of hardware, we now have a couple of extra things that are not done by us that are more commercial implementations. So the first one of these, keyboard didn't work, but the mouse did. The first one of these is Microsoft's CHERI. So this is taking our CHERI RISC-V architecture and trying to tailor it very much to a microcontroller use case. So they have a small amount of memory, and they have a very tightly integrated software stack. It was announced earlier this year and late last year, but it's all open sourced in February. And this is a big collaboration across the company. On top of that, Low Risk, who some of you may have heard of, their aim is effectively to be doing open source RISC-V work. They've recently announced that they're going to be producing an FPGA board based on this. It's still an FPGA, but that's more okay for a microcontroller. And so we're seeing that this is something that Microsoft and other companies are trying to productize as a way to get this kind of security into the microcontroller space. Also, a company called Codasip at the end of October, and then more recently at the RISC-V Summit a couple of weeks ago, had a presentation on this. They've also tried to productize CHERI RISC-V, this time targeting the bigger 64-bit applications class core. So the actual architecture they're going to be implementing is still a bit up in the air because we're closely working with them, but they want to put out a product that is a CHERI RISC-V core that you can just buy off the shelf, at least from them, and put into your products. But the big one really is Morello. So Morello is this big government, academia, industrial, multi-way collaboration, primarily between ourselves, SRI, who have been doing a bunch of work with CHERI as well, ARM, Google, and Microsoft. And so we have many millions, and the goal of this is partly to sort of break the deadlock between hardware and software, because at the end of the day, People don't want to write software for hardware that doesn't exist, and people don't want to build hardware if software isn't going to use it. They've been bitten by that before, and especially something like this that's quite complicated and disruptive, nobody wants to burn that cost if it's not going to pay off. And so by injecting this funding, the hope is that we can build this prototype hardware, we can fund the initial software development, and then try and get the ball rolling just to break that cyclical chicken and egg problem. So Morello, it takes the Neoverse N1 core. This is, if you ever use an AWS Graviton 2 instance, it's the core that they use in those. It also shows up in some Ampere products. It's kind of a few years old now, but it's sort of ARM's primary sort of scale-out big system core. And so in the case of Morello, it's running 2.5 gigahertz, it's quad core, it's out-of-order superscalar, all the things that you would expect of a real system. And so this, as you might guess, is one of these boards. There, the processor. And we have about 1,000 of these prototype boards manufactured. So then what about the software side? So that's mostly hardware. So the primary thing we have is this thing we call the Pure Capability ABI. So we have these capabilities, and the question is how we use them. The most obvious way is every single pointer that you write in your C code now becomes one of these capabilities. And this includes, by the way, uint pointer t, which has some interesting semantics if you want to talk to me about that. A very weird corner of the spec. Not only is it the language level pointers, but also all the pointers that you don't necessarily think about, but are quite crucial for things like security. So your return addresses, if you have C++, your virtual function pointers, GOT entries, your pointer to the stack. If you're using variadic arguments that live on the stack, that is also bounded, etc. So everything that could possibly be a pointer previously is now a capability. And this gives you the full sort of always-on Cherry protection that is what we advertise as being Cherry. And often we'll just call this Cherry C, Cherry C++, because Cherry Pure Capability C++, it gets a bit of a mouthful. So Cherry C, what we think of. And the result that we see is that generally most code doesn't really require any changes. Most code is compatible with this because we've tried to design it to be compatible with C, with C++. There's code out there that will make assumptions that no longer are true, such as they want to cast a pointer to a long and back, especially in the Linux ecosystem, especially in the Linux kernel. But outside of that kind of scenario, most code is generally pretty okay with this, especially if it's adopting uint pointer t. Then it tends to just work. The second ABI we have, which, as you'll note at the bottom, is something we say don't use, but we should acknowledge that it does exist, is the thing we call hybrid ABI. So we take our existing AArch64 ABI that doesn't have Cherry, and we say you can use capabilities, but you have to opt into it every way you want to use a capability. So we add this double underscore capability qualifier that you can shove on a pointer to say this is now a capability. If you're using uint pointer t, we now add this new uint cap t type that is the same thing just for a capability. But the idea is then this is ABI compatible with your existing code, and you can incrementally adopt it as you see fit. Using it in a widespread manner in your code, because you have to annotate every single place you want to use a capability, quite annoying. Right? You do not want to do this at scale. But in very limited cases, say you're interfacing between some pure capability code and some non-Cherry code, then it's useful because you can now express both types, and you can have that boundary and sort of take your old code, continue to run it, and then interface with new code. In terms of security, right, it gives you very limited protection because all those sub-language pointers, they're still integers. Every pointer that's not a capability is still an integer. And there's that DDC thing floating around, which is giving you access to every single possible address that the integers could want to use. So you have the capabilities, but they're not really giving you any protection, except when you're explicitly using them. It really is just there for interfacing. But it does exist. So I talked a bit about compatibility. So we're all familiar with the concept. You take your 32-bit application, and now you have a 64-bit OS, 64-bit system, and you want to run your existing 32-bit code. And so in the same vein, we can take existing non-Cherry 64-bit code, or in reality, hybrid Cherry code, and run it using the similar kind of compatibility layer to provide the same 64-bit system called interface, etc. But we can then also run our pure capability code on that same system. So again, we see the ability to do incremental adoption of Cherry in that respect. So again, right, this allows your existing binaries to run, but you're not getting any security benefit for those old binaries. You're just giving the ability to keep them working. In theory, you can do 32-bit on these systems. Like, there's no reason it wouldn't work. We just don't have any hardware that actually implements it. So one of the things Morello did is it took the ARM architecture and deliberately said, I'm not going to bother with doing 32-bit compatibility just because it simplifies things. There's no reason to believe it wouldn't work, but why bother to do it when we didn't really have a use case for it? Okay. So I said earlier, right, we had these bounds and these permissions were on the pointers, not on the allocations. So that means we can do interesting things with multiple copies of the same pointer. So generally, current security extensions that are dealing with protecting the allocations, so things like MTE, they're generally concerned with protecting going between allocations. But what they can't do is, say, have a pointer that's only to part of an allocation and another pointer that's to another part and another pointer that's to all of it. You either have to break it up or you don't. And sometimes we see that vulnerabilities are buffer overflows, but they're not between adjacent allocations. They're within an object. So an example might be you have an array inside your structure, and it's storing a string, and oops, you read into the string, and it overflowed into some adjacent data variable. Or similarly, you read out an adjacent value. And we would like to be able to protect against that, and we can. We can do bounding and even restrict permissions per pointer. And so we can optionally, if you turn it on, because it sort of flirts a bit with C compatibility and conformance to the standard, automatically insert sub-object bounds. So whenever you take, say, a reference to a field within a struct, we can then insert, well, this is the C intrinsic that you would write, but we can insert, now we're taking that pointer and we're adding on these bounds and restricting it down just to that array. So even though you go outside the bounds of the array, but within the allocation, you still take that exception because that pointer was only for the array. So far, though, this has all been about spatial safety and referential safety, which is this idea that you can't forge capabilities. But we also saw that use after free was a problem for a bunch of those DSAs. And the observation here is we now have this tag bit in memory. So if anyone's ever tried to do garbage collection with C, they quickly run into the problem that pointers and integers aren't distinguishable. So you have to be conservative. Anything that looks like it might be a pointer, you have to assume is. But now we have this tag bit that authoritatively tells you this is a valid pointer that can be used or this isn't. So what we can do is if you go and free a bit of memory, we can sweep all of memory and find every single copy that is referencing that bit of memory and then go and invalidate it. Now, you don't want to actually do it on every free because that would be prohibitively expensive to sweep your multi-gigabyte address space every single time you want to call free. So in reality, you batch them all up into some kind of quarantine. That allows you to effectively defer the free because you're saying nothing is going to reuse that memory. So although you can still reference it, that's fine. Nothing else is using it. It's as if you just called free later. And then at some point later in time, we have a sufficiently large quarantine, some fraction of your heap, some absolute size, whatever your policy may be. And then we go and just do one sweep of memory for that whole batch of frees. And so that allows us to do this efficiently. And we have some page table bits that are specifically there to try and accelerate it. So we are able to do this concurrently with the application still running because we're able to effectively in the page table say whether or not we've visited this page to do the sweeping. So a page that has been swept, you're absolutely allowed to use. A page that hasn't been swept, if you then go and try and read memory from it, is then going to trap and the OS is then going to say, oh, I better go sweep that page right now rather than whenever it decided to do it. So that gives us some form of temporal safety. Importantly, it's not use after free quite protection. It is use after reallocation, repurposing, whatever you want to call it. So that doesn't catch the use after free, but it does squash the vulnerability because nothing was using that memory in the meantime. The other thing we can do is compartmentalization. So historically, right, you have your integer, doesn't matter what part of the process is, you can just fabricate that, you can poke whatever you like if you know where it is. With capabilities, you have to have that capability and you can't forge it. That means if you don't give a bit of code a capability, it can't touch that bit of memory. So within one address space, you can now set up multiple different compartments with different sets of capabilities. They can only touch some subset of the address space that is their compartment, and you can share capabilities around when you want to share memory, but that gives you some form of compartmentalization. And with this sealing mechanism that I mentioned briefly earlier, that allows you to hand off capabilities that effectively allow you to call into a compartment but not use it for anything else. It is one of these opaque sealed things that you can't load via, you can't store via. The only thing you're allowed to do is jump directly to it, and that takes you into a well-defined entry point of the compartment. So by doing this, right, we're able to do compartmentalization within a process. Historically, you'd do it across processes. That would be a bit expensive if you wanted to scale it up, but now it's one process, it's just jumping around with capability, so it scales much better. And so we see sort of 1-2 orders of magnitude from performance improvement for IPC-style workloads, being able to do it within an address space versus between multiple processes. So examples, right? Maybe you want every single image you're downloading from your web browser, you don't trust it, you want to go sandbox it, you can now do that. Or every single time you open up a message in your mail application, that's a new sandbox. All these kinds of potential options for doing more compartmentalization suddenly become viable. But the one point about this, though, is that compartmentalization requires the software to be structured to support it. If you just have a tangled mess of code, there's no easy way to compartmentalize it. You need to be structured such that you can cleanly delineate where one compartment starts and when another one ends. So if your code is structured to do it, that's fine. If it's not, then there's a bunch of work to support it. Versus the spatial and temporal memory protection, memory safety, that is sort of automatic for free as long as you don't do horrible things with pointers. So in terms of the models, we actually have a couple of models that we're exploring. One is for doing compartmentalization within a single process using the library as the compartmentalization boundary. That's a relatively nice model that already exists. And so if you have code that's well written into multiple libraries, just having each library be its own compartment gets you some amount of protection sort of almost for free without having to think too much about the model. And then that's quite nice because if you want to transition between compartments, that just looks like your normal function call that happens to be in a different library. The other model we have that's trying to sort of map onto existing compartmentalization schemes is this idea of co-process compartmentalization. So effectively, you have multiple Unix processes, but they live in the same address space. That then allows you to do IPC-style workloads using existing approaches where they view the whole compartment as being a process, but you don't pick up the penalty of having to actually swap address space every time. So you can just directly jump from one to the other, potentially. So these have different trade-offs, useful in different cases, and in fact, you know, in an ideal world, perhaps you want to compose the two together. And so the inter-process library compartmentalization, that's quite easy to adopt, but has limited security benefits. The co-process one is a bit more robust, but requires you to have an application that's structured to be able to support it, but maybe fits into some of the existing frameworks that already work with processes. So our software stack, I'm afraid I'm committing a bit of a heresy here. We're not based on Linux. We're based on FreeBSD. So we have CHERI BSD, which is FreeBSD plus CHERI. So we have a FreeBSD kernel, we have FreeBSD user space, and we have a bunch of applications on top of it. Within the kernel, we are able to compile it with spatial and referential memory protection. What we don't have is temporal safety within the kernel. In terms of the user space, though, we have all three. So we can do spatial, we can do referential, and we can do temporal memory safety there. We have the co-process compartmentalization model does exist, but it's off on a development branch, whereas the linker-based compartmentalization model is in our mainline shipping release, and that just works if you opt into it. We also have hypervisor support, so you can run VMs, quite useful for debugging. That's relatively recent, and in fact, upstream FreeBSD doesn't quite yet have ARM64 support for it. We've pulled it in a little early, but it looks like it will land any week now. And as we talked about compatibility, right, we have this ability to run existing 64-bit non-CHERI AR64 binaries for FreeBSD or hybrid ones that fit into that same category. On top of that, we have a bunch of applications, so KDE, Plasma, some Wayland stuff. We have WebKit, we have OpenSSH, Nginx, etc. And below that, we're based on LLVM with our compiler, with our linker. We have GDB as our debugger. And so that gives us our full stack. Over on the right here, we have some of ARM's offerings that's a bit more early in terms of its quality. So they started off doing Android primarily as a nano Android that was just a headless Android. And more recently, they've been looking at doing distribution Linux. Those are both very early compared with CHERI BSD. They started later than us. They are working through just doing spatial safety throughout the stack. doing temporal safety is a goal, but it's a way off. Doing compartmentalization is a way off. I think they have some level of hypervisor support, but it's much less complete, but it's being worked on. And also at the same time, some groups within ARM have been doing versions of GCC rather than just relying on Clang, because Clang works well for the FreeBSD ecosystem, for the Linux ecosystem. Unfortunately, some things still assume that they are tied to GCC. They're not so portable across compilers, although these days it is getting better, especially with things like the kernel and glibc embracing other compilers. So a comparison then between high-level languages and CHERI C. So one answer people have for security is, let's just rewrite the world in Rust. And Rust is a great language. It solves a lot of problems, especially being able to statically detect a bunch of issues at compile time. But there is a lot of C and C++ code. So just using this website that tries to aggregate some open source repositories, right, it estimates about 12 billion lines of C and C++ in the open source ecosystem. The number is going to be way higher for proprietary code, and it's probably still missing a bunch of open source locations. That is a lot of code to rewrite in Rust, and even if you have some very competent developers, they are going to introduce a lot of bugs in the process. Right? That is economically not feasible in the short term. Even if you look at how many lines of Rust exist today in the open source ecosystem, it believes that there are about 39.5 million lines of Rust, many orders of magnitude less than C and C++. And in fact, that number is lower than the number of lines of C and C++ we have successfully compiled for CHERI C and C++. Right? So this just demonstrates the ability that CHERI doesn't solve all the problems that Rust does, but it's a very quick solution to solving a bunch of the very core problems. And absolutely, for very security-critical things, go and rewrite them in Rust, use better languages, do formal proofs, whatever your strategy may be. But let's just not say that rewriting Rust is the solution, because clearly, maybe in 50 years' time it is, but today it's not. And I quite like my systems to not be secure, to be secure within a 50-year time frame. So in 2021, we had this little 6-month desktop study that was run. We wanted to see how feasible was it to just take a desktop stack and try and port it to CHERI. A bunch of code of varying vintages, varying C and C++ language usage, completely different teams developing it. And we wanted to see, how awkward was it to make it work. So it was about 6 million lines across X11 and various KDE parts. And we saw this very minuscule 0.026% of lines of code needed to actually be modified. So that it was about, I think if you do the maths, that's about 1,000 odd lines of code out of those 6 million lines need to be modified. Very tractable, right? One engineer doing it part-time in 6 months is able to port some amount of X11 and KDE to just run, right? In this case, it was doing X11 forwarding within an emulator to an X server outside, but all the client side was ported, and you had a basic desktop environment just in 6 months. And we did some whiteboarding to look at the past vulnerabilities in Qt and KDE, and we found that if you included compartmentalization, about 74% of those vulnerabilities in the past could have been mitigated by CHERI. Interestingly, as you go up the stack, memory safety becomes a bit less important, and compartmentalization becomes more important for some of these larger scale systems to mitigate them. So it's important to bear in mind that that does need to be a problem that's kept solved. But we found about 74%. And so, as I say here, right, the observation here is that if you look at the threat models of these things, actually you do need to factor in compartmentalization, not just memory safety, if you have a language like C and C++ that's not inherently memory safe. So here's a screenshot from a real Morello system running a version of KDE. This is, if you go to the CHERI BSD website, this is what the image that I put up there was that I took. And so you can see, right, we have console, we have Kate as our text editor / rudimentary IDE, we have Dolphin. This is running with accelerated graphics through a Mali GPU. Firefox is not pure capability, but we install it on the system because it's quite nice to have a web browser. That is sort of one of the few things that we keep in the default install as not being pure capability. But it's there because you want it as a web browser. In terms of how you get this stuff, if you're interested in trying it, we have this one tool to rule them all, although we had one kernel to rule them all, so I guess I don't have that as the advantage of being first at that joke today. But this is sort of many, many thousands of lines of Python that's organically grown over the years and is intended to just work. You can, with this one command, you go run it, in this case, we want to run for RISC-V with pure capability, user space, and then we tell it to just build everything that it needs. So it will go fetch your compiler, it will fetch your emulator, it will fetch Cherry BSD sources, it will fetch firmware. Everything that you need to boot inside a QEMU environment will be fetched and built. Depending on your laptop quality, it will vary between like 20 minutes and hours, depending on whether you have a nice shiny new MacBook or not. So my MacBook takes about like 20 minutes maybe to build it. My previous one was more like a few hours, but mileage may vary. But it all just works and has stood the test of time. But that's not a great experience for end users, so we also provide specifically for the Morello system, right? We just, like Debian, we provide an installer image. You just download it, put it on a USB stick, boot it, and then you can just get up and running for those people who don't need to tinker with the OS or don't need to deal with emulators, etc. So we try and make it as user-friendly as possible, even though this is a research quality operating system. So getting involved. So why would you want to use Cherry even if you're not running on Cherry? Well, it helps you find potential bugs. Because if you can run your test suite and you run it on Cherry, it will tell you, oh, you actually had a memory safety issue here. Also, you'll find the places in your code where we're assuming things that we break. So one thing that sometimes comes up, people assume that pointers, surely they're not going to be bigger than 8 bytes, or surely they don't need to be more aligned than 8 bytes. A lot of allocators will just say, oh, I need an alignment, let me just shove in 8. That's good enough. Also, as I said earlier, right, a lot of people assume that UN pointer T and long or long or int64T are synonymous, and you can just shove a pointer into one of them and get it back at the other end. It's not guaranteed by C, but it is in fact okay with current hardware. We break that. We require that you use an actual uint pointer T because we need to preserve all that capability metadata. There are some other compatibility issues as well, but those are a bit more subtle. We've also got one of our boards donated currently to the GCC compile farm. So anyone who's used this, there's 50 or 100 or different development boards and systems that you can SSH into. It's open to anyone in the open source community who wants to work on open source software. You just go to the website, send them an email or fill out the form, and they'll get back to you, create an account, and then you can just log into any machine. And so we now have a machine running Cherry BSD Morello that anyone can just log into, try it out, try running their software. If you're a company and you're interested, there are a couple of avenues. You can go directly to the Digital Security by Design program and request a board. That is sort of a very free form, just here is what I want to do with it, and then they consider whether it's a good idea or not. There's also this Technology Access Program. That's specific to UK companies, but it gives you, especially for a small company, it gives you some amount of funding to actually go work on this rather than do it entirely by yourselves. And it gives you a little bit of guidance where you have sort of monthly meetings with people to try and make sure that you're making good use of the hardware, they understand what you're doing, etc. So a useful way to get involved. If anyone here is interested in either of these, though, please come talk to us. We can help you put in a good proposal, put in good words, talk to you about what would make sense to do, etc. And so with that, I have a demo. And I will also take questions if there are any questions. Yes?
Is there like a benchmark or something if we had the same chip which doesn't support Cherry with Cherry?
Benchmarking is complicated, in particular on Morello, because it was done on a very compressed timeline. I will try and highlight some slides. I have anticipated this. So it's the one thing everyone wants to know. So the short answer is we have a report that we put out, the latest version from September. It is online at this URL. We've also got a PDF snapshot of it published through the department's tech report. The headline figure is this graph, which is complicated because Morello is complicated. So the important numbers in terms of what the performance you can expect are these three ones. So these green and orange bars are trying to approximate the overhead that you can't have from Cherry by looking at what is just the overhead from the increased pointer size, because that is, we believe, what the primary overhead is going to be, right? It's what people see as the friction from moving to 32 to 64-bit, so surely going from 64 to 128-bit is going to be a concern. And so this just takes standard AArch64 code generation, but says that pointers are now 128 bits in size. There are some details for why it's not quite authentic, but it's an approximation. And so here we see about 3% on, it doesn't actually say spec. This is on SpecInt CPU 2006. running with training workloads because we're doing some stuff on FPGA, but the details aren't so relevant. But about 3% and 2% is sort of around about what you see just from increasing the pointer size in this hardware configuration. Because we have a first-generation prototype done by ARM, and it was done on a very compressed timescale because you want to get hardware out that then software people can use before the end of the research program, a lot of the normal design iteration process was cut back. So normally, right, you would design some chips, you would run some software in a simulation, you would then feed that back into the design process and repeat multiple times. But that takes a lot of time. And so the focus for Morello was not performance, it was primarily correctness and being able to model performance. So there's a quirk where we have to use this weird benchmark ABI that's not, in fact, the pure capability ABI, that is trying to work around one very specific microarchitectural issue that we believe could be entirely resolved. There are then 3 bars because there are some features in the architecture that are implemented a little bit inefficiently in Morello, in part because it's an old design that doesn't have to care about things like MTE. So some later ARM extensions cause the same kinds of requirements that we require in the microarchitecture, but because the Neoverse N1 didn't have them, they did a very sort of, hacky is not quite the right word, but a very sort of simplistic approach to resolve those issues where they overly pessimized performance to make it work without disrupting the microarchitecture. So the blue bar is if you take unmodified hardware and go and run with this benchmark ABI that's working around one issue. These red and yellow bars are if you go and work around one and then specifically a second potential issue in the hardware running on FPGA. And so this blue bar is about 15% on the unmodified hardware, but once you start to modify the hardware to address these issues, that's 7.4 and 5.7% respectively. So we have reason to believe that it's sub 10% performance overhead. It would vary on workload based on how pointer dense it is. If you don't have many pointers, performance should be pretty much unmodified. If you have a lot of pointers, you're going to get more overhead. But the headline figure should be sub 10%, maybe sub 5% as the kind of overhead.
Yeah, another stupid question.
Not stupid, probably, but
if it's around 10% efficiency, then does it make sense to like research in the way a compiler would do it rather than change the entire chip design? Like, would it? I don't know how much overhead would add for a compiler to do all these checks.
If you mean something like ASAN, it's much higher than 10%.
Okay.
So there are techniques to do it as compiler instrumentation, but they have A, higher overheads, and B, still aren't able to catch all the things that we can, because ultimately they're still having to deal with 64-bit addresses.
Okay. Thank you.
Yeah.
Thank you. I imagine that container off would be a macro that would be difficult.
So
can you talk about that?
So that is the textbook example for where subobject bounds breaks down. So there's this idea, in particular, you see it in things like linked lists, where you have your big structure, and then you embed inside it your linked list, sort of link pointers data structure that's a generic thing. And then you pass off pointers to this nested object to the linked list implementation. And then as you iterate, you then say, okay, well, I know that the pointer I've got was inside a bigger data structure. Let me go back to the bigger data structure. So that's the case where you really don't want the subobject bounds. So we have compiler annotations using GNU attributes that let you say for a specific field or a specific type, don't automatically insert subobject bounds for this field. There are also intrinsics that explicitly say, I want to do an address of operation, and even though the type you think you should, you still don't in this case. So there are various ways to work around it, and in fact, in the CHERI BSD kernel, we enable subobject bounds because actually a lot of kernel-level attacks do exploit this kind of issue. And so we face that issue because container of is a thing that you see in kernels. We have done some annotations on container of so we can statically catch most of those issues at compile time where it says, oh, it looks like you're doing a container of, but you didn't annotate the field. You should probably go fix that. But most of the time when we see a crash in our pure capability kernel is because there's somewhere that's doing subobject bounds that shouldn't have. Yeah. Okay. So anyway. In terms of demo, I kind of slightly bamboozled you. This was the demo. This is a live system.
I've
Yes.
got one quick question.
It's right under there.
So when you write through one of these capability-based pointers incorrectly, what happens?
Right, so we have some demos. Right, my first buffer overflow. We have an array of 5 integers from 1 through 5. We have a secret 42 next to them. And we read in an argument from the command line that says, which index of that big array do I want to read? So if I go and compile it, well, first of all, let's compile it not for Cherry. And then we go run it, and we give it 1, and it gives me back 2 because, well, I started at 1, not 2. I give it 4, it gives me 5. And then I give it 5, and oops, it gave me out that secret value 42. I now go recompile for Cherry. And just to convince you that it does still work, I'll give it 1, and it still gives me back 2. I give it 4, it still gives me back 5. As soon as I go back 5, it gives me this thing, which is a signal. So if I go run it under a debugger, I now take a trap here. Well, I wrote it unhelpfully where you can't actually see the variable for the result of A to I, but I can tell you if I go look at the instruction and you squint your eyes and ignore the fact that it's ARM assembly, W0 is 5, right? Our index is being shifted by 2 because we're using integers, and if we look at this capability, which is also data, we can see we have the bounds here that are just those 5 capability values. And in terms of the reporting, it gives us this new sigprop we've introduced, and it tells us it's a bounds fault.
So following up with that, is it possible to write code sensibly such that any buffer overflow that is there, you can at least trap and handle within your program? So rather than it being a security problem, you're not just turning it into a DOS.
It would be very awkward to make it recoverable in the general case, because at the end of the day, what you do, you'd have to now fabricate a capability. Where we see the DOS problem being mitigated is from compartmentalization, because if you have a buffer overflow within a compartment, you can go kill that compartment, restart it, and the rest of your application potentially can continue on. So that is kind of our solution to the problem. Okay. I also said we had temporal safety. So if I go and build a use after free issue, ignore the do alloc do free, that's just to hide from the compiler so it doesn't optimize too much, because it would just then want to say that, well, I just returned 43. I go allocate some memory, I store 42 in it, I then free that memory, and then I increment the value in that address, right? So typically you probably think without any kind of use after free protection, that's going to give you 43. And in fact, if we go and run that now, it does indeed give me 43 because we have this quarantining. We're not on every free going and revoking. I have this magic, and I need to read my notes file to tell me exactly what the flag is. There's this magic environment variable you can set if you really want to enable every free to revoke. Do not do it except for debugging, but it is useful for tracking down these issues. Now I can go run it, and again I get one of these security exceptions. In this case, it will tell you it's a tag violation because the tag's been cleared. In terms of other demos, yeah, I mean, we can go run uname, right? It's a FreeBSD system. It's running a pure capability kernel, etc. Got a whole bunch of processes in the system. I've added this column that says whether or not it's pure capability. So ELF64C means pure capability. And oh, look, everything is except HTOP itself, because for some reason the package wasn't available last night. I don't know why. It's built fine in the past, but I guess something went wrong. But everything else is running just fine. What else do we have? We can go do this statistics of all the processes in the system. This is specifically dumping out a bunch of revocation information, if I can use less correctly. So in particular, on the right-hand side, you see this epoch value, which is how many revocations have I done. And so a whole bunch of processes. KWin has done hex 11c. I don't know what it was before the talk, but maybe it's done some more. Ocular's done hex 25e. Ocular is not the most efficient PDF viewer, etc. So this has been doing temporal safety this whole time for the talk as well. We talked about the buffer overflow use after free. The final one, VMs. I can go boot another instance of Cherry BSD, runs uboot for a few seconds, and then suddenly brings up the FreeBSD loader. I can go run it, boots, and then in a few seconds I'm at a login prompt, and I have another Cherry BSD instance running live inside a VM. So then the final demo, it wouldn't be a computer if you couldn't run Doom. And so indeed, let's not make it too hard for myself. There we go. There is Doom, and if we go back to our HTOP here and go find Crispy Doom, so there you go. You can see Crispy Doom L64C running as a pure capability process. And so with that, are there any more questions with the 1 minute I have left? Great. Thank you.